of the BLEMO's one, Dr. Meruch. I will also acknowledge the presence of all other directors of National Meteorological and Hydrological Services. Ladies and gentlemen, good morning. All protocols observed. I hope everyone had a good evening, as good as what I had. I believe I've missed out on a fun evening, and the football last night made up for that. And we looking forward to even a greater game of football tonight. I believe everyone is with me on that one. My name is Ezekiel Sebego. I work for the South African Weather Service. I have been asked, or I have been entrusted with the responsibility to present to you on the Southern Africa Regional Flash Flood Guidance System, which I believe is a topic that is quite relevant to an occasion like today. And it is a program that can benefit a lot from what has been discussed already in this program and what will be discussed in future presentations. So this is the outline of my presentation. I'll start with a definition as per the BLEMO of what is a flash flood. We will then look into the background of the flash flood guidance with global coverage. It is a program by the World Meteorological Organization together with its current funders. It is a program that is looking out for more funders, and we hope that out of these events, deliberations, we will be able to get more funding and spread it to other parts of the continent. It is called with global coverage, but as you will see in my slides to come, it is not quite covering the entire globe. I believe with global coverage was intended to be, that is the goal that we should work towards. I will then talk about the system architecture thereof and then bring things closer to home. That is Southern African Flash Flood Guidance System, or FFGS. I have a few case studies, two from South Africa and one from Malawi, on the operational use of this system by weather forecasters. We'll touch a bit also on the roles of different agencies in FFGS. In one of yesterday's presentations, there was a discussion regarding between the Met and the hydrology, where does the one's role end and where does the other start. And I believe that the definition of what the flash flood is will hopefully give us a clear guideline in terms of, in an effective way, who can be responsible for what. As meteorologists, we are responsible for things even before weather starts happening, and the definition of the FFG of flash flood will tell us that things happen very quickly, and I am hoping that we will all be convinced that as much as it's a hydrometeorological issue, but with more emphasis on the meteor side of things. And from meteorology, of course, our work. We will then talk about FFGS additional components. So currently in Southern Africa, we have FFGS in sort of a plain format. There are, however, other advancement or other plug-in modules, or if we may use, say, motoring terminology, some turbocharge that can be put into the current FFGS to achieve the desired results. So what is a flash flood? So according to the World Meteorological Organization, a flash flood is a flood of fluctuation, however, with a very relatively high peak discharge, in which the time interval between the course of the event and the flood itself is less than 6 hours. So it rains and it floods all within 6 hours. And I hope you'll agree with me that by this definition, the role of meteorology is quite strong in there. Of course, it's flooding, so there is a role for hydrology, which I will explain later on in my consequent slides. So we all need to work together towards being able to predict this. And This system is intended to also address other issues or to supplement the presentation that was done by my colleague or on impact-based forecasting. She mentioned that same amount of rain over different areas can result in different impacts, and the flash flood guidance is trying to support that. According to the UNDRR, floods and flash floods in general account for over 40% of all natural disasters that occur in the world. And next to that is severe storms, which some of those or some of the impacts that they cause can actually be flash flood as well. In South Africa, we define severe storms as storms that can produce either a heavy downpour, of which the impact will be flash floods, or large hail or strong damaging winds. In terms of the background of the FFGS, so it is basically a tool that is used by forecasters. It is designed to provide them with readily accessible observed as well as forecast data. So it works on observed data as well as forecast, because we would like to issue warnings before things happen. So it's not only about what is currently happening. It's what is currently happening and what is expected to happen in the next 6 hours. In some cases, there are projects from FFGS that gives a outlook of up to 24 hours. And we have been in certain forums previously, and we had feedback that people would like to receive warnings much longer than that. And our explanation to that was that this is just one of the tools that is used in the National Weather Services to warn the public. So a typical example is a large weather system is expected. We could issue a media release many days ahead, but closer to the time, we would then be able to plug in this FFGS to be able to pinpoint the areas that will be affected, as well as the levels of impact that would be expected out of that system. It is a system that is not just plug and play for forecasters. There still needs to be engagement by themselves. As you will see in subsequent slides, it's similar to numerical weather prediction models. It is not reality. There are still inherent errors in the system, so forecasters still have to apply their minds into this, take into consideration also the errors that may come with the input that goes into, or rather the limitations that is inherent in the input data that goes into it. With regards to flash flood guidance with global coverage, the main objective is to advance the capacity of weather services to forecast the potential occurrence of meteorological hazards, namely flash flooding, as well as other subsequent hazards that may result from that. In other parts of the world, or in many parts of the world, which is a phenomenon that is increasing, we see secondary impacts like landslides and rockfalls, and FFGS is designed to be able to assist in those. This is just an overview of the current programs that exist around the world. So obviously closer to home, Southern Africa, I will zoom in on the subsequent slides, but the current footprint is only over areas from the Zambezi Basin southwards. So that is Zambia, Malawi, Mozambique, and south of that. It is a program that is developing quite well. My subsequent slide will also, or rather on this slide already, as you can see, there's some planned expansion, Central and Western Africa, as well as over the Southwest Indian Ocean islands. So Madagascar, Seychelles, Mauritius, as well as the Comoros. There is planned expansion of this program to reach that. Currently, 15 regional projects are ongoing, and how it works is national centers, and there also needs to be a regional center who will then have the delegated responsibilities. Some of those will include the actual running of the FFGS models, the collection of the observations in real time that are needed for ingestion into the system, as well as the production of the numerical weather prediction models that are used into the system. So there is good news in terms of expansion to our neighbors in the islands that's planned for later this year. There has already been an opening meeting to that regard to introduce the project, but it's still in its infancy stage. Also over Central and Western Africa, there is some movement towards there. However, the part or most part of the content still remains open, and it is also something that we all need to work towards addressing, taking into consideration the impact or the severity of flash floods and the role that they play in terms of affecting the world. Into the FFGS architecture, the image on the right is just a snapshot of the interface as forecasters look at it. However, we'll go into the individual elements of the architecture. The main one, of course, is the input side. The main factor, as you can imagine, will be precipitation or rainfall. So that is either observed and also, or both observed as well as also forecast. The observed rainfall plays a crucial role in understanding the current existing conditions, so that we may be able to identify areas where there is potential for flash floods. Due to the current situation with the status of observations, the primary source of rainfall estimation currently is with satellite rainfall. It has its advantages, and of course, it has its limitations. One of its advantages is, of course, the coverage. The entire globe is covered by satellite footprint. However, in terms of estimating rain out of satellites, it is still something that is being developed. There is planned improvement in that regard. There's a lot of work that is done. There is currently the deployment of the Meteosat third generation, wherein there is expectation of much better improved products, which will be used as inputs in an applications that is important, such as this. In areas where there is radar, of course, radar does play a crucial role in rainfall estimation, also given its inherent challenges like the range. It can only useful range of only 250 to 300 kilometers. So a large country would need multiple radars for that to be able to be covered. And of course, it comes with its operational elements as well. It needs a lot of power, it needs more stable power rather, and it also needs regular maintenance. Rainfall gauges, those put in real time, are crucial for a system like this. We saw by the definition of a flash flood, it's a flood that event that occurs within a very short space of time. So it needs to have inputs on live reporting, automatic rainfall stations, in a format that can be ingested into the system in real time. There are then other input elements like temperature, evapotranspiration, of course, GIS data, land use data, and images for that. Okay, thank you. Then it goes into, that would be the input data. And as you can imagine, a system like this is only as good as the input data that is put into it. There's a saying called that goes garbage in, garbage out. So it is very crucial that the input that goes into the system be of as good quality, as well as granularity in terms of time intervals, as well as spatial granularity. So it is very important to have that good input into there. Then go into the modeling side of things, which is where hydrology comes in. Then there are subsequent products out of that, land surface products, and then up to a stage where then the forecaster starts to play a role that is into the threat product as well as the warning products. So the forecaster would get one of the first products that they will get out of the system is a product called the actual flash flood guidance. So the flash flood guidance, it says over this basin, this is the amount of rain that is needed to cause a flood within the specific time period. So for this system, we use 3 hours as well as 6 hours. So it will say this is the amount of rain, given the rain that has already fallen and other environmental conditions, you need this rain in order to cause a flood in this particular period. Is then the forecaster using both numerical weather prediction as well as their own experience and knowledge of their local condition to say, will I get that amount of rain? And if the answer is yes, then the flash flood side will be positive, which means that particular basin for that particular time period, there can be a flash flood expected during that. And that is the main part where the forecaster will then have their inputs, which will then lead to a formulation of a warning, which will then use the system that we presented on yesterday with regards to impact-based warnings. This particular flash flood, where is it happening? Is it in a highly populated area? What time of the day is happening? And those factors will be taken into consideration when that warning is being issued. I've zoomed in now onto the Southern Africa as it currently exists. So it's from Zambia, Malawi, and South of that. I just picked one of the fields from the FFGS as it stands. So in Southern Africa, we have had this since February of 2014. So it's exactly 10 years that we've been using this system. However, locally in South Africa, we had a zoomed in version thereof, which is called the South African Flash Flood Guidance, so the SAFFG. Without the R, it was concentrated mainly over the main over the major cities as well as over the Cape South Coast. That was done through the sponsorship by the National Disaster Management Center. And this is just a comparison between the two systems. The SAFFGS, as you can see, doesn't cover the entire country, the main population centers, as well as over the southern parts of the country. It uses radar as its primary quantitative precipitation estimate input. With all the challenges that I've mentioned, there's always satellite as a backup for that, as well as those rain stages that are reporting live. The resolution is quite higher in terms of spatial as well as time-wise compared to the regional one. The regional one is also still used in South Africa, of course, because not the whole country is covered by the high resolution one. There is currently work being done to upgrade portions of the regional one over South Africa where there are radars. So places like over the central parts of the country, as well as in the northeast where there are now currently radars, to upgrade it to the level of the SAFFGS1. And I believe with all the resources available, that would be the approach for the rest of the countries, that whichever countries do we have radars, it can then be integrated into their system, as rainfall estimates plays a crucial role in this particular application due to the nature of the phenomenon that is flash flood. On to the case studies now, we've picked 3. So the first one is in Letaba, that is in the Limpopo province. This happened in 2014, so that was just when this project or this program was launched in South Africa. And of course, we had to also say something about the KwaZulu-Natal 2022 flooding event. This particular one is the second one, which happened in May. So there were two events. The first one was in April, and exactly a month later, there was a repeat of the extreme weather. We also received some input from our colleague in Malawi, who they are also using the system. They recently experienced a severe flood in their country, and they made use of the system to be able to issue the warning. I'm just touching high levels in terms of the case studies. So as a background, around the 5th of March in 2014, there was a tropical weather system which affected the Letaba area. So Letaba is situated in the northeastern parts of the country. The rivers and streams were quite full, and some of the dams there were concerns of the dam walls breaking in those areas due to the heavy rains that experienced. So I picked a few of the SNAP products out of the SARFFG. So the concentration will be over the northeastern parts of the country. So the image on the top left, that would be the mean area of precipitation. So that is the amount of rain that was measured at that particular time. The particular field is for 24 hours. So on that morning, those areas had already experienced some areas were over 150 millimeters of rain. And subsequent products next to it is the soil moisture, which areas of interest will be appearing in the blue, which means total saturation, and thus with a high risk of flooding. The ultimate third product will be the one on the bottom right, whereby the system is indicating that given the rain that has already fallen and the rain that is expected, the amount of rain that is needed to cause flood, or the amount of rain that is needed to cause flooding will be exceeded, and that comes out in those particular basins as the ones that there is flooding can be expected. And then forecasters will then use that as a way to issue warnings for those particular areas. The images as they are now, I left out some of the geographic information, but the application can be put in geographic application as it came from the developers. And within the region, we have the capability of adding more geographic information like roads, schools, and other points of interest to make the system much more usable for the forecasters. Sorry.
Yes.
Apologies for that.
I think it's a projector issue. Yes, please. Apologies, everyone. I think there's a projector issue. Oh, shit.
Thanks for you.
Okay, apologies for that. So that was the conclusion of the Letaba case. On to the KwaZulu-Natal case. So I put this slide as well to complement what my colleague presented yesterday, just to show this is just the tool that I used to the eventual product, which would be a warning like that. So this was the eventual warning that was issued for KwaZulu-Natal. As she explained yesterday, we used the impact-based warning system. In our case, we do make use of numbers. So in this case was the worst possible scenario, high likelihood of severe impacts. So the impacts that we came up with was firstly widespread flooding and widespread flooding of road and settlements, danger to life due to fast flowing streams, and that was all derived using all the tools that we have available at our disposal, including the FFGS for the period. So these are the products that were in use at the time. Obviously, KZN being the area of focus during the day. The map on the left is the mean area of precipitation. So that is the rainfall that has been measured. So for this particular area, there is a radar in place. So radar would be the primary source of rainfall estimation during the period. And you can see the thread product on the right-hand side. That is where the basins which we expected to be flooding came out, highlighted. Of course, what happened during that period in that area was well documented. There was quite widespread destruction that did happen in those areas. The last case was from the central parts of Malawi, which was 2 months ago, end of February. Forecasters in Malawi, they used the FFGS tool. So the area of focus is over the central parts of Malawi. There is highlighted over there. And on this particular case, also the main area of precipitation. So it started with the rainfall that had already been measured by the system. They use mainly satellite rainfall estimation as primary source of rainfall estimation. They do have some reporting ground stations which report live to the system. Those are then integrated with satellite rainfall estimation. At the later stage, they are used for bias correction of the satellite as the ground truth is nothing better than that. So they found the tool to be quite useful and they used that to be able to use the warnings. Late in the day, there were flash floods. However, there's still people who lost life due to other factors that we also discussed yesterday, some of which they listed as failure of people at risk to take action after the warnings have been issued. And some people just ignored the warning. So there is still some work to be done in that regard. However, the tool itself works very well. Notwithstanding the fact that even if we issue warnings and beautiful forecast with actions, it's not taken, all of that is all in vain. And so we still need to address the matter of the last mile as well as the actions that needs to be taken. In conclusion, just to touch on the roles of different agencies for effective flash flood forecasting and warnings. I have already inherently spoken about the roles that weather forecasters play, so we'll go to other role players. Hydrologists contribute expertise in understanding the behavior of working environment. The setup of the system itself includes a lot of hydrological inputs, as well as the continuous improvement thereof. We provide insights into the watershed dynamics, runoff processes, as well as flood risk assessments. Disaster management, of course, after the warnings have been issued, they are the ones who are responsible for the dissemination of the warnings for the emergency preparedness prior to the event happening, as well as the response once the event has happened. The last portion of my presentation talks about the additional components. So we thought this would be the perfect platform to highlight this potential enhancement to FFGS as it exists currently in Southern Africa. These do exist in other parts of the world, but currently not in Southern Africa. One of the first things that was highlighted was the fact of most of the flooding actually happened in urban areas. The FFGS, as it is currently, does not take those into consideration. So the assumes everything is all natural basis. There is no concrete and all of those. So the matter of urban floods still remains the potential area of improvement in our system, taking into consideration that globally there is quite a lot of urbanization that is happening. So it's a matter that we will really have to take into consideration. There have been some innovation, as we said there, in Indonesia, in Turkey as well as in India, where in the east that urban flash flood warning system that's been developed. Another element or another enhancement factor that needs to be factored into place is the river routing module, which obviously means taking over from the small river streams for which FFGS caters for towards the main river streams. So that is also a module that is available, but is not currently in place for all of the countries. I'm speaking under correction. I believe my colleagues from the Department of Water and Sanitation are here. There is currently some work that has been started in South Africa in the Val and Orange River system. I see a lot from the colleague at the right. So that is an enhancement that is currently in place, which obviously would be desired to be in place in all areas that do experience floods. The last of the potential enhancement is the seasonal to sub-seasonal and summer prediction, which currently is under development in Central Asia. So they were one of the first implementers of FFGS, and they are now moving into much longer time scale for better preparedness by all concerned. Finally, this program has been in existence globally for over 12 years, and 4 or 5 years ago, there was a commission independent review by WMO in terms of how it's operating currently. Out of that came what is called the FFGS sustainability strategy to make sure that the system is used to its full potential where it exists, and most importantly, is rolled out to other parts of the world where it doesn't currently exist. And these are just some of the factors that they had that they are key in for the success of the FFGS to be sustainable worldwide. Some of those included a developing of an inclusive and broad governance model. So it is a system that was developed in the USA, and in the previous governing models, it was only the developers and WMO who was involved in that. So the sustainability strategy is asking that all role players be involved in the governance model, and in particular that they be in-country ownership of the system to make sure that it is used to its full potential. There was then a call for an increase in training efforts for the users, increasing the visibility, as well as developing of additional financial and human resources. So, as mentioned, the system was developed by the Hydrologic Research Corporation in San Diego, and they have been doing all the work. So, what the sustainability strategy is calling for is that there be other role players included, the different centers of excellence around the world in different elements that contribute to the FFGS. There is a center of excellence for satellite rainfall estimation, for example. They're doing excellent work, which the results thereof can be used as input into the FFGS. There are other centers of excellence for numerical weather prediction models, which is in the UK Met Office, and their output can be useful in the sustainability of the FFGS. There's also a call for inclusion of academia in the program itself to make sure that it is developed much better. In conclusion, FFGS is just another model that's similar to numerical weather prediction models. And systems of this nature have their challenges, and as such, that needs to be taken into consideration by the users thereof. It is currently made available only to weather forecasters who have been trained to understand, for example, the weaknesses of numerical weather prediction models, and which is one of the main inputs into the system. I do believe there has been requests from other agencies to access the system, which it can be made available, taking into consideration the level of interpretation that would be needed in order to make optimal use of the system. I have mentioned before as well that the system itself is as good as what goes into it. The main factors there being the quantitative precipitation estimation, so how much rain is falling. Currently using the satellite where it is available, using the radar, and use of ground rain stations as well where they're available, as well as the precipitation forecast. One of the challenges that we have identified with the system such as this is, in some cases, very small scale weather events, which can be very severe. Due to the limitations of the input that it received, it will not be able to resolve. So I was very happy to encouraged to see the colleague yesterday presenting a numerical weather prediction model with 3-kilometer resolution, which would then be geared to be able to resolve such small-scale weather features, and such an input will be crucial to a system like this. Of course, it's not only on the precipitation forecast side of things, it's also on the rainfall estimation. So if we have that with the radar, we would then be able to resolve such small-scale weather phenomenon, which, by the way, is also one of the basic needs for having an urban flash flood guidance system over an urban area. You need a very high resolution input in terms of observations as well as precipitation forecasts. Some of the recommendations would be making of case studies and presenting the achievements or the capabilities of a system such as this to a forum like this one. I thank you. Thank you very much, and apologies.
Many thanks, Ezekiel. So we have about 10 minutes for questions. If anybody has any questions?
Thanks very much for your talk. It was very good. I was curious, you mentioned briefly in the middle of the talk about impact-based decision support based on some of the flash flood guidance. And I just wondered if you have any observations about some of the specific challenges getting impact-based information to be able to formulate that based on flash flood versus a more steady flood event.
Yeah, so gathering of impact on the ground is a continuous challenge that we continue to face, but something that positive that came out of impact-based forecasting was we were able to forge a close working relationship with disaster managers who are the people on the ground, where of course they are well equipped. And that was one of the positive gains that we got out there. And we did indeed get a lot of feedback in terms of that. Also from the general public, there has been a lot of videos and photographic materials that has been received. Of course, that we take with great caution in terms of there are, of course, some people with malicious intent who would circulate things from the past. Within our work environment, there is one image that we know every time when it rains, people will start circulating as if it's a representation of what is currently happening. But in general, I think once we started issuing warnings, mentioning the potential impacts, it encouraged the people to start reporting those impacts, whether they did happen or they did not happen, or they happened more severe than it was forecasted. So it had that spin-off in terms of people now not only concentrating on what the weather was, but then also what the weather did. And that, of course, also taking into consideration the initiative by WMO to actually develop for countries to start developing databases of actual impacts of the weather. We do for sure have a lot of information in terms of what the weather was, but what the weather does, it's something that we are looking forward to documenting systematically. And we believe that with social media and other streams, we are getting quite useful information for use in verification of the warnings.
All right, thank you very much for the presentation. Maureen from Ghana Regional Agency. You mentioned in the presentation that the FFS system was almost similar to the local weather prediction system. So, what is actually the model behind this FFS system? And producing this forecast to the users, is it mainly done by the South African Met Office, which is by the meteorologist or by the hydrologist? That's what you thank you very much.
Yes, so the warnings are produced by the Met services to the public. So there are different types of models that I use. So firstly is the numerical weather prediction model. So how much rain is expected. There is then the hydrological model that is used for modeling the hydrological response or runoff response from the basins once the rain has started falling. So that part is handled by the hydrologist, but then it has also because it's a model itself, it's not a representation of reality on the ground. It has its limitation. It is used, or it is based on the information that was input in the beginning of the projects, which there could be evolution during time, and it may not be a true representation of the current system as it is. And then, of course, the numerical prediction model has its own limitations, some of which we mentioned in terms of resolving of small-scale features and all of that, and other atmospheric processes that are not accurately resolved within a numerical prediction model.